We're going to demonstrate the Torque toolbox for you. This is a suite of tools that you can use to estimate the resources for a particular quantum algorithm running on a specific quantum computer configuration. So I'll show you how to do that. First, I'd like to draw your attention to the execution buttons in the toolbar specific to running the Torque tools. The first on the left is Options, second QAFL-C, then Generator, Control, FTQEC, and Resource. So these buttons control execution of the underlying software tools. First, let's go to Options, and here you can configure the running of the tools. There's two things you should consider. One is you're running a large problem size. You want to minimize the amount of computer memory and writing to disk that occurs. If you're running a small problem size, you don't need to worry about that. And so for the examples today, we're going to run a small problem size so that we can show all the features of the toolbox. So in addition to the two default boxes that are checked, we're also going to check synthesize and generate SVG images. Under generator options, we're going to have the generator keep the circuit files so that we can examine them later. And then we're also under PMD options, which is the physical machine description. We're going to select the superconducting qubit, or SQC, and save that. And for our first example, we're going to look at one where we're describing 3 adds. So it's our 3-adder project. So let's open up the folder. And you'll start with 2 files. So one is a configuration file that basically describes the problem that we're executing. And these parameters will guide the tools, and they will also be in any final output. So you can correlate the numbers in the output with the nomenclature of the problem description. There's also the 3x3.qfl or QAFL file, and QAFL is our quantum programming language. So let's open that, and we'll open that with the QAFL editor. And so this is an Eclipse framework, and we have a plugin that understands QAFL syntax, and then therefore keywords are highlighted. Also, if there's a syntactic error, that will the editor will identify that and bring it to your attention with an error message. But as you see here, we're declaring basically 4 quantum variables. Then we're adding the first 2, and then we're adding the second 2, and then we're summing the results of the first 2 adds. And so now we will go back and open this QAFL file again, but now we'll use the default Eclipse editor, and now you'll see a number of differences. So if you look up at our execution buttons in the toolbar, QAFL-C is now highlighted and Control is highlighted, but the others are still gray, and that's because the Eclipse environment now recognizes the existence of the data files needed to run those tools. If you go to the bottom of the work window, you'll see a number of tabs. One for the QAFL file that we're looking at. The next one is for the experiment config file that I just described. And as these tools run and produce other data files, they will appear in tabs at the bottom here for quick access. You can also access these files by going to the project folder on the left, from which we originally opened the QAFL file. Okay, and now we're going to run the QAFL-C compiler and then examine the output that it generates. Okay, so it generates a Quiggle file. That's basically a quantum circuit description language, and that's the QGLX file. It's an XML file, and so you notice that it's quite verbose. And next we'll look at the HTML file. And this is basically a summary of some intermediate steps of the compiler. It's mostly used for debugging and understanding the execution of the compiler. So first, it identifies kinds and types, and this looks pretty similar to looking at the quaffle file with the quaffle editor that's syntax aware. We can also go to the quaffle plus resource tab, which is the middle tab. And here it basically shows the QuiggleX on the left. So notice there's now terms such as wires, and then there's also procedure calls. And then on the right is a nomenclature that we use for computing the resources in various dimensions, such as the number of T-gates, which would be count T, which is second from the bottom, the T-depth, which is the last one, and also things such as width max and width delta at the top, which is the maximum number of qubits used, and the incremental use of qubits as it goes from stage to stage in the circuit. Another thing that we'd like to do is look at the actual circuit. And the default HTML viewer here does not support that, but if we go back to the HTML file and right-click, we can open it with the web browser as opposed to the Eclipse default editor. Now we will go to the tab labeled Side by Side, and this will allow us to compare the original quaffle program to the various intermediate stages as the compiler acts on it. So first we'll look at the far left where we have the original Quiggle program. And as you notice, we can mouse over the variables and we get a window that gives us the variable type. And so that variable type we know is an unsigned integer of 3 qubits. And here we can look at another variable. It's an unsigned integer of 3 qubits. And you can actually see the value, or the initial value of the variable. To the right of that is the Quiggle or circuit representation of the program. And here you can see types such as wire, which are basically specific to describing a circuit rather than a high-level program that talks about data structures. You'll also notice that there's 3 procedure calls here. So these are functions in the programming language that have not yet been expanded into a concrete circuit. In the next column, the .qc, this is another circuit format, again with the embedded procedure calls. And then to the far right, we actually have a rendering of this circuit. So you can see the 4 NOT gates at the left-hand side of the circuit, and then you can see the 3 labeled boxes, which are the procedure calls that you can see in both the circuit description language and in the high-level programming language. So the next step in the process is to call the generator, and the generator will now call a series of circuit libraries to expand these procedures into concrete circuits. And these libraries are either specific circuits or they're generator functions that are parameterized by such inputs as the number of qubits or vector length. After running each of the tools, you should see a message in the log window that says finished, and also it'll give you the time that it took that tool to run. So when you get large circuits, some of the runtime will be in the seconds, whereas now it's in the fractions of seconds. So there are some new data files that were generated. The QGLXE is basically the Quiggle circuit in XML expanded, so all those procedure calls were now filled in with concrete circuits. So we can go to the QLR file, which is the quantum logical resource file, and it basically shows that there was a procedure which was the unsigned in-place modulus add, and each add required 16 T-gates with a T-depth of 8, and the maximum width or maximum number of qubits used was 7. And then the instance circuit specification here shows that combined, the 3 adders plus the other gates required 48 T gates with a T depth of 24 and a maximum width of 13. So basically the algorithm that's being employed right now is to minimize the number of qubits, and therefore the circuit is mostly serialized in execution. Now we've taken a Quaffle program and we've compiled it to a concrete circuit, and we've counted a number of gates and other parameters of interest to us. We looked at the logical resources in terms of number of qubits and T gates. So now we will go and look at the physical system side, and then we'll put the two halves together. Now we're ready to run the control tool. This will take the physical machine description, or PMD, and generate a bunch of controlled gate operations with specific error characteristics. Underlying the control tool is an optimal control search algorithm, and then the fault tolerance tool will use these gates and their error characteristics to compute the fault tolerance resources. As you notice in the log window, the tool is running. It takes a little while for the optimal control search algorithm to run and then to characterize the Pauli error channel. As you notice, the control tool has now finished. There's a message in the log window, and it looks like it took 1 minute and 25 or 26 seconds, which is typical for the PMD that's described or modeled here. Now that we have the output from the control tool, we'll take a quick look at that. So that is the PGS file, or primitive gate set. And so you see Pauli error characteristics, you see the pulse duration, and then you see some kind of classical measures of control resources in terms of max power and slew rate, as well as the gate time. So now we will go and run the fault tolerance tool, which uses these gates and also uses the logical resources that are required for the algorithm. So the fault tolerance tool is finished. If we look in the log window, we note that it took about 1 minute and 13 seconds, which is typical. And now what we'll do is we'll run a script controlled by the resource button, and that will take the information from the fault tolerance tool as well as from the logical resource counts, and it will produce a number of values that basically describe the different parameters, different resource parameters. The output is basically a QRC file, and that's what's displayed right now. But we can also go look at this information in table form. So rather than look at the table information for our small 3-adder example, we're going to look at something a little more interesting. And this will also allow us to compare some different problem sizes and also compare different physical machine descriptions. So if we go to the experiment folder, and you see here that we've run a number of experiments with different size problems for the triangle finding algorithm, and then also we've run it with 2 different PMDs, one an ion trap PMD description and one the superconducting qubit PMD description. So now we'll go and click on the Show Table button. And first we see a Controls tab, and this allows us to select the columns of the table that we want to view. So we'll turn off the some of the parameters associated with the fault tolerant component. And now we'll click on the VRE spreadsheet tab at the bottom, and this will bring us to the table. And here is the data that we pre-computed. And we've run triangle finding with n equals 5, 10, 15, and 20. And we've run those cases with both the ion trap PMD and the superconducting PMD. And as you notice when you look at the data, the threshold, the fault-tolerant error threshold for the ion trap PMD is much higher than the superconducting PMD, and therefore it will require less resources. And now we'll start looking at the data and see those examples. So if we look at the number of qubits in T-gates and T-depth, right, they're going to be the same for the different PMDs because those are just logical circuit information. But you see those dramatically increase as the problem size increases. Next, we'll look at the column labeled distance L, and this is the levels of state distillation. And so you'll notice that for the superconducting qubit, there are 3 levels, where the ion trap only requires 2 levels. And now we'll scroll to the far right of the table and look at some of the physical resource requirements. We're now looking at the far right columns, which contains the calculations of the physical resources and algorithm runtime. But note the first 2 left-hand columns, we've retained the information about the algorithm and problem size with respect to the variable n, and we've retained the physical machine description, superconducting qubit or ion trap qubit systems. So now let's go look at the runtime. We notice that with increasing problem size from top to bottom, the algorithm runtime increases. We also note that for each problem size, the superconducting qubit architecture is much faster than the ion trap architecture. And this is because of the faster gate times for the superconducting qubits. We also notice that the resources required, the number of qubits, is higher for the superconducting qubit relative to the ion trap qubits for the same problem size. And then this is due to the higher error rates. So this type of analysis provides very important insights to the physical machine description effects on the total quantum computer resources and the total algorithm runtime. The last thing we want to look at is saving the information from this table. So if we go up to the Save Table button, it gives you a choice of whether you want to save it in CSV format or JSON format. So we're going to select CSV, and we're going to save the file. And then after the file is saved, we're going to go start a spreadsheet application. And now you see the data displayed in our spreadsheet application. So this enables you to generate pictures and graphs and other types of displays or pictures that you would want to include in a report. And this concludes the demonstration. I encourage you to go to the QID User's Guide and begin exploring on your own.